Hello, astronomy students. The purpose of this video is to discuss quickly how to solve this homework assignment and go over a couple of hints about areas that you might get stuck on. So this homework assignment is pretty straightforward. It involves a conversion problem and the definition of velocity. But let's dig into what you need to do to get it done. So in question one, there's two parts, and both of them involve making a conversion from the cosmic calendar, which is measured in cosmic years, and the Julian calendar measured in Julian years, basically Earth years. Okay? So the idea is that we want to have a conversion. We want to have a way to say, this is how many, seconds there are in the cosmic calendar that correspond to a, say, Earth year. So let's set that up. So let's go ahead and think that one of the main things that we're interested in is days on the cosmic calendar, because we're told that an event happens on May 8th on the cosmic calendar, and then we're also asked for the date of an event. So what we really want is a conversion from a cosmic day to a number of Earth years. All right? So let's just discuss how to do that conversion factor, and then I'll give one other tip about an area that you might get stuck on in part B, and then we'll be done with problem one. So the key idea here is that a cosmic year is 13.8 billion Julian Earth years. All right, and Julian Earth year is just the standard that's used in astronomy for these particular types of constants, and it's the one that's used for leap years, how we have the extra day every 4 years, because sure enough, there's a quarter of a day every year, so it adds up. All right, so let's go ahead and think about that. If we have 13.8 times 10 to the 9, all right, so that's this 13.8 billion, and then this is going to be Earth years, that's equal to 1 cosmic year. All right, so EY for Earth years, again, that's Julian Earth years, and CY for cosmic years. So, okay, so far so good, but we want to have cosmic days. Well, we know that there's going to be 365.25 cosmic days in every cosmic year, just like, days in an Earth year. So that idea is going to hold on both of our types of years. So what we want to do is just divide both sides by 365.25, do the same thing over here. So 365.25, and what that's going to give us is the number of Earth years in one cosmic day. All right, so we'll go ahead and I'm going to go off screen to make this calculation, and I'm just going to type into my calculator in scientific notation 13.8 times 10 to the 9, and then go ahead and divide all that by 365.25. All right, so that's going to give me on the left-hand side, so this is going to be Earth years, and it's going to be, looking at my scientific notation here, I have 3.778. So 3.778. I'm not picky about significant digits, but generally you don't want to add them. In this case, I guess I am, because everything was given at most, or the minimum of 3 significant digits, and here I'm putting 4. But again, that's close enough. All right, so 3.778 times 10 to the 7 Earth years for 1 cosmic day. So CD. All right, so with that conversion, all we need to do is just count the number of days from January 1st up to May 8th. So figure out how many days that is, and then you can then say, okay, well that's how many cosmic days it is. Multiply that number, maybe let's just say, for the sake of argument, May, January, February, March, April, May. So about 5 months. 30 times 5. So we're talking, somewhere in the range of 150 days. So you would simply multiply that, that number right here, the 3.778 times 10 to the 7, multiply that by about 150, and that's going to be the number of Earth years in that many cosmic days. So you go from the beginning of time, the Big Bang, so the very beginning of the day on January 1st of the cosmic calendar, up until May 8th. All right? And we assume if the date's given, it's the beginning of that date, right? Because I don't give you a time on that day. All right, so then what's the extra thing you need to consider for part B? Well, all you need is that here we're going back in time. So the same idea that I mentioned from counting from January 1st up until May 8th. Well, it's similar here, but you have to go the other way, which can trip people up, all right? So, okay, let's take a look at this. So one theory says that a large impact between an asteroid and Earth created the moon 4.53 billion Earth years ago. So same idea as we want to say, okay, well, we have the number of Earth years. So we have, 4.53 times 10 to the 9 Earth years. And if we divide that by this value right here, our conversion factor of 3.778 times 10 to the 7 Earth years. Now, here's the cool thing about conversion factors. Before, I wrote it as an equation, but you can rewrite it as a, conversion factor by just dividing both sides by none other than CD. Of course, would cancel it on the right-hand side. We have to do the same thing to both sides of the equation. And then we just have that 3.778 times 10 to the 7 EY over CD just equals 1. Well, you can always multiply any equation by 1. It doesn't change anything. So that means that it is our conversion factor. And sure enough, we just put it right down below. That's going to cancel out our EYs. Since our CD is in the denominator of the denominator, it's going to go up top. And that means that we have effectively converted 4.53 times 10 to the 9 Earth years into cosmic days. All right. So same idea on the conversion factor, but it's maybe slightly less intuitive by going from Earth years to cosmic days rather than cosmic days to Earth years. But that wasn't really my main point. My main point is that once you have that value, which we'll just say here, so we find the value. I don't want to give it away, but once you have it, in this case, you don't count those days from January 1st because you're going back in time. We're talking about an event that happened 4.5 billion years ago, right? That's the key difference. So instead, you need to count backwards from December 31st. All right, so then the last step is we'll say count the number of cosmic days because your value is going to be in CD. All right, so the number of CD backwards from December 31st. All right, so then just count the number of days backwards. You can look at a calendar and just count them backwards. Do a Google search where you can say, okay, if you're starting at 365, because here, since we're interested in full days, I just want the calendar day. You don't need the 0.25, all right? And it's not going to affect the value. It's not going to be the difference, right? And so once you just take the 365, you need to find out how many days you got, whatever your answer was from the division here involving the conversion factor. You just count that backwards, subtract that number. Let's just say it's 90, which I don't think is close to right, and then subtract that from 365. Well, 365 minus 90 is 275. We'll just look up what the 275th day of the year is, or again look at a calendar and find out yourself. All right, but a quick Google search could always be like, what is the the 200th day of the year, right? So that's the idea here. You just got to remember to count back from December 31st. In case that wasn't legible, it's December 31st. All right, so that's it for our conversion on the cosmic calendar, or rather converting Earth's calendar to the cosmic calendar. Cosmic calendar, not a real thing, right? But just a convenient way of conceptualizing the huge amount of time that has elapsed since the Big Bang. All right, so on to number 2. Number 2 is all about the definition of velocity. So the key idea here, the key equation, if you will, is none other than V equals d over t. V is velocity, and I'll read the problem in a second. D is distance. Sometimes you can think of it as length, right? But distance or length is interchangeable. And t is time. All right, now with our equations, you always want to convert over to what are called the base units of the metric system to use the equation. Then you might want to convert back to something else, or maybe you don't need to convert to anything because everything was given in base units and you want the answer in base units. But the key key thing is every time you use an equation in a science class or in science in general, you want to convert over to base units to use the equation. In this case, velocity, meters per second, not kilometers per second. Distance is going to be in meters, and time is going to be in seconds. Sometimes you can get away, right? Things cancel out nicely by not converting, but that's a bad habit because you're likely to get it wrong in that case. So play it safe and always convert to the base units. They're called the base units for a reason. They're the foundation of the metric system. All right, so we got our velocity. It's given in kilometers per second, so we would want to convert that value over to 1.065 times 10 to the 6 meters per second. Now, the idea here is that, I just know that we have 10, maybe it's 10 to the 5, actually, because I'm going to add 3 more zeros to get the kilometer. So I'll fix that and point out what I'm doing here in my head. Is the kilometer to the meter is a difference of 1,000 to 1. So if I'm converting over to the meter, I'm moving the decimal place over 3 places. Well, if I'm going to convert this scientific notation in the first place, it starts over here at 2. So initially, it'd be 1.065 times 10 to the 2 kilometers per second. But then adding an additional 3 decimal places is 10 to the 5. In other words, it's 106,500 meters per second. All right. If it was times 10 to the 6, it'd be a million, but it's not a million. It's just 100,000. All right. So that is our velocity. We have a time that we also want to convert over to seconds, and this is real important. All right. So our time is given in days, and if we convert it over to seconds, then we simply need to find out how many seconds there are in a day, and that's going to be, in this case, 8 times 24, because there's 24 hours in a day, and then there's 60 minutes in an hour, and then 60 seconds in a minute. So this is going to be your number of seconds. In other words, it's 8 times 24 times 60 times 60. So whatever that number comes out to be is your time in seconds. All right? And so then we're going to have, that's going to be how far light travels in that amount of time, all right? Because let's take a look and, as I promised, read the question, right? Because we need to use this definition of velocity, right? So we definitely need to use this key idea here, this key equation, but we also don't want to get ahead of ourselves because I'm asking you to do 2 steps, but it doesn't necessarily, look right at first glance that it does. We're actually required 2 steps. So how long would it take a spacecraft with a speed of 106.5 thousand, are not saying it very well, 106,500 meters per second, right? To travel the distance that light travels in 8 days. Aha. So how far does light travel in 8 days? All right. So that means we first need to find out how far does light travel in 8 days. All right. So how far does light travel in 8 days? All right. So we would go up to our equation here, but we need to rearrange it to answer this particular part of the question because the definition of velocity, v equals d over 2, great foundational idea, but sometimes you don't care about solving for the velocity, like this case right here, at least in this step. We instead want to solve for the distance. So I would want to find d equals v times t. And I'm not going to use the v of the spacecraft, not in the first step. I'm going to use that in the second step. But I want to use the speed of light. Speed of light is always defined as c. Now, that might not be immediately obvious as a velocity, but you get used to it. It's one of the big constants you always see. C in uppercase G, all right? Well, which you'll see in the next number. Now, c for the speed of light, very particular speed, always the same. It's called the speed limit of the universe. Great way to describe it. And it is none other than 2.99792 times 10 to the 5 kilometers per second. In other words, it's about 300,000 kilometers per second. Okay, well, if that is, our speed here, then we want to think about, how fast, or in this case, how far does it go, right? So it's simply what you'd want to do is find your d for light, and it's going to be c times t. And do you want to convert your kilometers per second? You bet. Yeah, I always have to do that. And so here, I'll round it a little bit. I wouldn't recommend rounding it, but just for the sake of not having to write out all the digits, 2.997 times 10 to the 8 meters per second. All right, so that's going to be my value for C that I'm going to plug right down into this equation down here. All right, into here. And then I'm going to multiply by T, the 8 days, right, but converted to seconds. That's going to give me my D value. Then I'm going to plug that D value into the velocity equation, but this time you might use my converted spacecraft velocity to solve for T, because both times we're actually not solving for velocity, so both times we're going to rearrange it. So step 2 is then how long, right, which is going to be a time, does the spacecraft take? All right, and so in that case, it's simply going to be a matter of, get that a little bit more clear, I'm going to be solving for T. So if I want to solve for T in this equation, imagine that I cross multiply. So I multiply both sides by T. That's going to cancel it out on the right. But then I also want to divide both sides by V. So there we go. So the V cancels. I got the T by itself. So then you can see that T is just D over V. All right, so we'll go ahead and write right here. So T is D over V. All right, so you'd plug in the D that you found in the first step, plug it right in there, right? Plug it in, and then divide by the velocity that we mentioned at the very beginning, the converted velocity of the spacecraft in meters per second. There you go. There's your time. I don't specify if I want it in seconds. I often do tell you what I want the units in here. Here you can give it to me in any units, but as it's been laid out, once you solve for that time, it will be in seconds. If you want to convert it back over to days, more power to you. I think that's a great idea. You might even want to convert it to years. It's going to be a lot of seconds. All right, and then in part B, considering that Jupiter is located a distance, okay, so we're being given a distance here from Earth at opposition, which is the orientation of the planets. It means that, opposition for Jupiter would be that, Jupiter is going to be away from us in a direct line with the sun, right? So in other words, like if you were to draw a line from the sun to Earth, a straight line, and then that straight line would continue and hit Jupiter. So there'd be a straight line that would connect Jupiter, the Earth, and the sun. That's the particular orientation where the planets of Earth and Jupiter are at opposition. All right? And how long would it take a laser beam of light from Earth to be bounced off Jupiter and return to Earth? So quickly to wrap this up, we would have Earth right here, we would have Jupiter up here, and then we'd have a distance between the two, but we know that the light needs to go to Jupiter and then come back. So I could draw that like you going to Jupiter, bouncing, and coming back. So that means that our total distance is 2D. So right, we could just use 2D in our equation, and then we know that our velocity is C, right? Our 2.997. I believe a lot of times it's right as 3.00 because that's what it rounds to with 3 significant digits, but 2.997 to use 4 significant digits times 10 to the 8, right? Meters per second. I know kilometers per second are great for describing the speed of light, but not great for making calculations. All right, most of the time. Now, okay, so great, we got that so far. Then all we need to do is solve for T. We already know how to do the algebra to rearrange the definition of velocity to solve for T. So then we would just want to find T, right? And that's how you would wrap this up, right? But remember that here your D is actually 2D, right? So we could say that this is our D, and then we are going to be rearranging an equation that looks like C is big D over T, right? And then we're just solving for T, all right? So hopefully that clarifies the approach, gives you some solid hints, and helps you if you're stuck on this homework. Thank you so much for watching this video. I hope you find it helpful.